All right, the next way we're going to compare series is through the limit comparison test. So here we don't have to say sequence A is less than sequence B. We just have to know that all the terms in both of the series are positive, and we also have to have that the ratio A sub n over B sub n, well, that limit is L, and L is not 0, right? So it's some number, it's not infinity, not 0. So that's really important. If you can do that, then they either both converge or they both diverge. So that's pretty nice. So the trick here right? So positive meaning not 0 and finite meaning not infinity. So the trick here is choosing the second series carefully. So just like before, this doesn't have to be true for every term in the series. It just has to be true for all terms past a certain point, right? So maybe it's true for all n larger than 100 or n larger than 4 or all n larger than, 3 trillion. Okay, so let's check this one out. So we're going to use the comparison test. So we're going to so here we have A sub n is equal to 1 over A sub n plus B. So we know that A sub n is positive, so we needed to do that. And then we also need to find a B sub n, right? So now we're looking for a B sub n. So the thing that we want to compare it to is going to be a known series. Like we know the geometric series converges. We know that P series converge for P greater than 1. We know the harmonic series diverges. And this one feels a lot like 1 over n, right? It's a little bit different. It's the general harmonic series, but let's compare it to just 1 over n. So if we let B sub n be 1 over n, then we know, first of all, that B sub n is greater than 0 always, so that's good. And then what we need to do is we need to apply here the limit as n goes to infinity of A sub n over B sub n. And so that's going to be the limit as n goes to infinity of 1 over an plus b over 1 over n. And then you can simplify this to the expression, the limit as n goes to infinity of n over an plus b. And this limit is really easy to evaluate. It's just going to be 1 over a. So 1 over a, because we have here that a is positive, then this is finite, not equal to 0, and it's positive. So we're good there. So we've met all of the requirements by carefully selecting B sub n to be 1 over n. So now what I can say is that the harmonic series diverges. Therefore, the generalized harmonic series also diverges. right? So if we had compared it to a convergent series and met all the requirements, then I would have concluded that the general harmonic would also then converge. But just to show that they both have to do the same thing. Okay, so you just stack them on top of each other, get the limit. If it's not zero and it's finite and it's positive, great. Now you can just kind of assess based on the known quality of the series that you picked. So let's try another one. So here, this one's kind of interesting because we're going to have to think carefully about what you might want to choose as your B sub n. So when I look at this, I might consider if you were to consider, say, the harmonic series, right? Again, because you might think, okay, if I have a 1 over n, maybe this will, I can show the limit comparison test and get something nice. So if I consider using then, okay, each term is positive. And now let's look at the limit. Then I would have the limit as n goes to infinity. And I would have 1 over n divided by the square root of n over n squared plus 1. And it doesn't matter which one's on top and which one's on the bottom. So if I do that, then I could shake this all out, and I would get n squared plus 1 over, what I get? So n to the 3 halves. And so here, I would see that this limit, if I do this, this is going to be going to infinity, right? So because the power of the numerator is greater than the power of the denominator, this thing goes to infinity. So this doesn't work. So we cannot use the harmonic series. Right, so we cannot use the harmonic series. So another series we might consider using, and yes, I'm intentionally choosing bad ones just to show you. So you may consider using the geometric series, because we have an n squared on the bottom. Sorry, a p series with p equals 2. So we have an n squared on the bottom, so we might do something like this, right? So then I would have here the limit as n goes to infinity of 1 over n squared divided by root n over n squared plus 1. And so I would get that I'm taking the limit as n goes to infinity of n squared plus 1 over n to the 5 halves. And you're thinking, okay, this is good. This isn't going to infinity. The problem is that this limit is 0. So we cannot use the p series with p equal to 2, right? Because remember that the limit has to be finite and strictly positive. So we can't allow it to be 0. Okay, so the real trick of this is going to be looking at the powers of the leading terms in the numerator and the denominator. So what we should do is we should consider just looking at the leading terms. So just look at root n over n squared, right? So that's going to be equal to 1 over n to the 3/2, right? So this is the thing I want to use. So use a p-series with p equal to 3/2. And we know that when we have a p-series and p is strictly larger than 1, it's going to converge. Right, so we know that the generalized p-series, so we know that p-series converges for p greater than 1. So I'm going to use a p-series with p equals 3/2, and I'm going to run it through the limit comparison test and see if we get anything good. So let's go ahead and do that. So now so if I do this, then I'll get the limit as n goes to infinity. And I hope it's obvious that each term is positive since n is positive. So we've already cleared up that requirement. So the limit as n goes to infinity of 1 over n to the 3/2 over the square root of n divided by n squared plus 1. And so working that out, taking the limit, we're going to get n squared plus 1 on top. And then on the bottom, I'm going to have the square root of n times n to the 3/2. So that's going to be n squared. And this limit is 1, which is great because now we have that the limit is finite and positive. We know that a sub n and b sub n are also positive. So we can determine convergence or divergence of the given series, which was this, based on our p-series with p equal to 3/2. So again, we've checked that a sub n and b sub n are positive. We've taken the limit of them, a sub n over b sub n, shown that it was 1, which is both finite and positive. And now what we're going to do with that is we're going to say, okay, if p-series with p equals 3/2 converges, the thing that we used, then the original series must also converge. So our conclusion here is that the series of the square root of n over n squared plus 1 converges.